We have flash.
ICCSA.
Okay. Which one? This one? Okay. Okay.
Okay, I sit here.
Yeah.
Oh, sorry. It's
Just one moment. We need
okay,
to
okay.
share it.
Yes, yes, of course. Entire screen, maybe.
Yeah. No, I think it should be this one, right?
No, just
This one?
yeah.
This is?
I think
Yeah.
so. Okay. Do you hear me?
Yes. Okay, no problem. You can start. Find your presentation and you
They are hear me?
Yeah, we can.
yeah,
Okay, thank you.
So I think,
Do you see my slides?
yeah, everything is perfect.
Okay, okay. Hi, my name is Lena. In this presentation, I will share with you our work monitoring CO2 in seismic data using neural network. Carbon capture and storage is a technology that injects supercritical CO2 into the subsurface geological formation for permanent storage. The goal for doing this is we emit into the atmosphere. Into the subsurface, it will lead to a series of physical responses. It will form a gas saturation plume, and physical properties such as density and seismic velocities change. And we need to monitor this process in order to ensure that injection is safe, to determine the initial pressure and location of the injection. Numerical simulations such as multi-phase flow in porous media and seismic modeling are the essential tool for solving CO2 storage problem. This is necessary to predict storage capacity and assess the long-term risk arising from fault activation and well-burn leakage. However, it is very
Прием. Меня слышно?
Я слышу.
Я
Можем
слышу.
общаться, да. То есть система работает.
Okay. These two?
Yeah.
Yes. After you open, please share this.
Share my screen.
Firstly, you can open your PowerPoint. Okay,
Is it
you
PowerPoint?
can put it into the slideshow or whatever. Okay.
Share
Zoom
screen.
Yeah. Share your screen. I think it should be here, right? Okay, here is the next presentation. You can start and introduce yourself.
Mhm.
Hello. Can you hear us? I mean,
Yes. Do you hear me?
yeah, that's great. So I think we can proceed.
Okay.
Right?
Let me.
So
Yes.
and you're our next speaker, Daniel Kazidyanov.
Uh-huh.
He's,
Thank you very
from
much.
Nazarbayev University. So go ahead.
Thank you very much.
from the university, I spot by myself. And that is why sometimes it means disconnected.
Can I look at, sorry, can I look at
Yes, of course.
Sorry to interrupt you.
Because we don't have internet connection like yesterday. No one comes here for connection.
Okay, but it seems that you have
It's okay.
Yeah, it's because
You're using your
connected.
Okay, please. Thank you.
If you want someone that.
Yes, I understand. Yes.
No stable connection?
No.
Ah, the same, okay.
Okay, you can start.
Okay. Okay, I will continue. Maybe then they'll connect. Yeah. And so in today's presentation, I will present how the power law parameters of non-Newtonian fluids influence the CFD dam simulations of fluid-driven fracturing process. So this work has been done in collaboration with Yerlan Amambek at Nazarbayev University. So injection of polymer solutions is a common practice in many subsurface applications, such as hydraulic fracturing, enhanced oil recovery, and groundwater and soil remediation. So when the pressure of injecting fluids exceeds the mechanical strength of the rock formations, the fracture initiation can occur. And so there are many factors affecting that fracture initiation. So it depends on the fluid properties and rock heterogeneity and solid particles like solid formation properties. But in this study, we focus on the fluid rheology, and CFD dam is a common popular tool to investigate these processes. But accurate time step should be selected for accurate, for convergence of the simulations, and the things becomes more complex when dealing with monotone fluids and viscosity, non-linearity in viscosity results in many numerical challenges of those simulations. And this work is based on our previous study on fracture initiation. In that work, we investigated physical fracture initiation mechanisms. And here, specifically, we focus on how power law parameters of non-Newtonian fluids affect the fracture initiation and morphology, injection pressure, evolution, and time step sensitivity. First, I will describe the numerical model formulation, and then we'll show some numerical settings, and then present key results and finalize with main conclusions. In our study, we represent the rock formation as a porous granular medium containing many individual particles, and these particles are simulated using discrete element method. And in discrete element method, the motion of the particles is governed by Newton's second law, and interaction between particles is described by Johnson-Kendall-Roberts model for weak cohesive contact forces. And fluid flow in porous media is described by locally averaged Navier-Stokes equations. And the total particle fluid interaction force is the sum of all forces acting on a single particle from the surrounding fluid. And the dominant component of that interaction is a drag force, and that drag force specifically is adapted for power law non-Newtonian fluids in our study, and fanning friction and particle Reynolds number contains power law rheological parameters, which can relate the fluid rheology into the momentum exchange with particle. And in our study, we use separate methodologies to calculate the time step for solid phase and fluid phase. In the solid phase, we use Rayleigh time step criterion, which is based on material parameters of the solid particles. And for CFD time step, we use Coron-Friedrich-Levy CFL condition and diffused time step criterion. And the diffused time step criterion is specifically for creeping flow regime, where the Reynolds numbers in much lower than laminar flow. And usually in CFD and then time step, the solvers operate at different time steps. And the coupling interval shows the ratio between those time steps. So rheology of the injecting power law solutions is described by power law model, where the viscosity varies with shear rate, and it also influenced by consistency index and flow behavior index. And consistency index shows the overall magnitude of the viscosity, and flow behavior index shows how viscosity changes with shear rate. For example, in Newtonian fluids, for example, water, where viscosity is constant, n equals to 1, and n equals to 1 at any shear rate. And when the n lower than 1, the regime is shear thinning behavior, and viscosity decreases with increasing shear rate, which is objective of our study. And when the n higher than 1, the regime is shear thickening, the behavior is shear thickening, and viscosity increases with increasing shear rate. And this slide shows the simulation settings of our study, and we reproduce the Haley show experiment by injecting fluid into the sample under stress. And in our study, in our numerical model, there are 45,000 particles, and material parameters of the particles are provided at the table on the right. And here we use 5 different consistency indices from 1 to 5, and each consistency index has 3 flow behavior indices. So total simulation cases 15, and okay. Yeah,
you can use pointer.
Yeah. So here we use overall total 15 simulation cases, and then discrete element time step is the same for all simulation cases, and it was calculated based on a Rayleigh time step criterion. And for analysis, we use 2 CFD time step cases, actually 10 of the -5 and 10 of the -4, and with coupling numbers 1 and 10 respectively. And flow type is transient, incompressible, laminar, and the solver is piezo-based for CFD-DEM coupling. And the composition of the parallel computing, like core composition, is based on a domain size, and we provide many cores for like a longer direction over here. And our sample, we use anisotropic stress conditions. For example, higher stress is applied from the top and lower stress conditions applied from the sides over here. And here's the software that we used, and here HPC system. So actually, it's not running. Oh, see. Okay, so there should be a video animation of the fracturing, but I think it's an old version. So I will skip this slide. I will show the snapshots in the next screens. So actually, this slide shows the snapshots of the fracture propagation cases. So the main fracture propagation cases. So at flow behavior index 0.2, the consistency index 1 doesn't create any fracture or fluid infiltrate into the surrounding medium here. And at K of 2, there is a linear orientation of the fracture, which is perpendicular to the lower applied stress. And K of 5 shows a radial pattern, which is independent of the stress and shows a radial pattern of the fracture. And when we increase the flow behavior index to 0.3, K1 shows the two linear fractures, and K2 changes from linear to radial fracture, and K5 still remain in radial fracture, but larger fracture surface. And this slide shows the velocity and viscosity fields during the fracture propagation, and left figure corresponds to the linear fracture propagation, and right corresponds to the radial fracture propagation. And from the velocity figure field, we see that there is a higher concentration of the velocity at within the fracture and fracture tip, and due to the higher velocity gradients, there is a lower viscosity within the fracture, and significant changes in viscosity shows that there is a higher infiltration into the surrounding media over here. And at higher consistency index, velocity is lower within the fracture, and the fluid affects the particles uniformly and exceeds the stress applied from the sides, and therefore our fracture behaves in radial pattern. And as you see from the viscosity figure, there is few changes in the viscosity, which means that there is a limited infiltration, and fracture propagates. Fracture propagation is mainly governed by particle displacement regime. Injection. So this slide shows the injection pressure results. At the maximum point, we have fracture initiation begins, and injection pressure decreases as the fracture grows, and increase in consistency indexes results in higher peak pressures, but overall pattern is the same for almost all cases. And this slide shows the injection pressures results for different flow behavior indices, and increase in N results in higher peak pressures, but the pattern also different over here, and the increase in N influence the fracturing opening rate. For example, a rapid decrease in pressure corresponds to the higher fracture opening, and gradual decrease in moderate opening, and stable pressure evolution with time indicate that there is no fracture at all. And this slide shows how the power law parameters influence the time step sensitivity. For example, for example, a figure on the left, lower like flow behavior index are similar as in both time steps, like over here, but at higher 0.3 flow behavior index, there is a significant discrepancies in pressure results between like these time steps. And as you see, the discrepancies occur starting from about like 5 like seconds, where the fluid is already stabilized, like in steady state, and the viscosity is increased. And here we calculated a relative error from our pressure results, and from the figure we can see that lower flow behavior indices, even at higher consistency index, results in lower errors, but increased consistency index results in higher relative errors. So this result shows that flow behavior index has pronounced effect on time step sensitivity compared to consistency index. And here is our main conclusions. So let's summarize. Fracture morphology depends on fluid rheology. Low viscosity leads to linear fractures. High viscosity results in radial fractures. And flow behavior index has stronger impact on time step sensitivity than consistency index. And simulation with lower flow behavior index shows accurate results even at higher time steps, but higher flow behavior indices require smaller time step for reliable results. So here's our references. Thank you very much for attention. If you have questions,
We've got 1 minute for questions or comments. Is there any?
One question. I have a question. A question about the boundary condition that you applied for the
fluid
stress.
Stress. Mm-hmm.
Because at the top I see that 2000 Pascal. Yeah, here. And from both sides it's like 1000, 1000.
Yeah.
So why you didn't apply the same boundary conditions?
Yeah.
Both sides.
Actually, yes. There are other cases where applied like isotropic stress conditions, but to see the effect of the fluids, usually anisotropic stress conditions applied. For example, if you apply same boundary conditions, and the fracture propagation is still radial even at lower consistency indexes. So we don't see the linear propagation. That's why we apply that. We observe at different stress conditions.
Thank you. Okay, thank you. Okay, maybe one more.
Do you have questions?
One dozen.
So thank you once again. We need to proceed to the next speaker.
Okay, thank you.
Okay. The next presenter, please.
So the next speaker is who is next presenter?
Okay.
Please go here. You can, I think you should firstly stop sharing the previous one.
It's only sharing the slide, yes?
Yeah. And right now you can share yourself.
Where is the share?
This one. I think, have you opened your slideshow?
Yes.
If so, you can start. Okay, can you see the screen?
I hope everyone can hear
Here
me.
we can see it.
Can you see the screen? Good morning, everyone.
Make it full screen presentation, please.
Full screen?
Yeah. The presentation mode.
The presentation mode.
Here. Stop sharing. That's entire screen. I think. And
Okay.
I think it's
Now everyone can see the entire screen. I hope.
Yeah, I think so.
Okay, let's get started. So good morning, everyone. My name is Dalit Kalish from Nazarbayev University in Kazakhstan. So I'm pleased to present our recent work, Physics-informed Kolmogorov-Arnold network for modeling two-phase flow with experimental data. So let me briefly introduce the motivation behind this work. So in many subsurface and reservoir engineering applications, modeling two-phase flow is essential. For example, in enhanced oil recovery and CO2 storage and contaminant transport and others. So these systems are mostly governed by nonlinear PDAs with complex boundary behavior. While traditional numerical methods like finite difference, finite volume schemes are powerful, they often require strict meshing and stability conditions. So in recent years, machine learning has increasingly been used to model this kind of complex physical systems, where the system has non-linearities, limit data, and multi-scale features. So that's where comes the physics-informed neural network, or PNNs, offering the mesh-free and data-driven way to solve this kind of equation by enforcing the partial differential equations directly into the loss function of the neural network. Our objective of this research is to explore the effectiveness of the newly introduced Kolmogorov-Arnold network within the PNN's framework to model two-phase flow in porous media. Specifically, we aim to solve the Buckle-Leverett equation using the both Kolmogorov-Arnold network and the MLP, the multilayer perceptron-based PNNs, and compare the performance of both architectures in terms of accuracy, training efficiency, and generalization. So to evaluate this, we use experimental data involving the fluid dynamics. Also, we investigate how different architecture and training strategies affect performance of our network, newly introduced. And ultimately, our goal is to assess whether CAN is a more robust, interpretable alternative to model nonlinear partial differential equations in fluid dynamics. So this is a short outline. We'll start with the background of, I'll introduce you with the background of two-phase flow and Buckle-Leverett equation, then introduce our neural network and architectures, and also we'll examine the results and evaluate the performance of both models and summarize our findings. To model two-phase flow in porous media, we begin with the fundamental equations governing the fluid movement. The first is a mass conservation equation, which ensures the change fluid mass over time. In this case, we make the under standard assumptions like incompressibility, no sources or sinks, which is simplified, shown in the presentation. Then we apply Darcy's law, which relates to the flow velocity and to the pressure gradient with relative permeability and viscosities and absolute permeability for each phases. For phases, we choose oil and water. Then it goes the phase mobilities, which express how phases changes. And finally, the saturation constraints of the phases. It's a necessary condition for two-phase systems. As a result, it resulted with discovering equation, Buckle-Leverett, one-dimensional cases. For this Buckle-Leverett equation, we made this. We introduced dimensional variables and made some substitution to normalize and make it suitable the equation for further analysis. And with the current fraction of flow, non-convex case, because the non-convex case describes the more complex behavior of the fluids. And the following boundary conditions in the boundary and the initial conditions. And also for final equation, final PD, we incorporated diffusion term as it was proposed from the prior studies from Olga Fuchs. Then I'll introduce the neural network itself. The idea of this physics-informed neural networks, that neural networks approximate our solution by with trainable parameters under this enforcing this loss function consisting of two composite loss functions. The first one is ensures that the neural network fits the data of the boundary in the initial conditions. The second one is the partial differential equation itself. So this neural network was integrated with these two different architectures. The first one is the MLP. In MLP, it's a standard fully connected feed-forward neural network. It is widely used, and it uses a simple simple linear transformation with non-linear activation functions. It uses another principle. It was the idea behind of the neural network was after the Kolmogorov-Arnold representation theorem by fitting the data, not the neuron, the splines. It's a activation function that changes the spline and the biases and also the weights. So the difference between this, that the multi-layer perceptron uses the fixed activation functions, while CAN fits with the learnable activation functions, which is changes over the training. So we adjusted the following setups for our both architectures, and we represented the results. To verify our models. We compare it with the analytical solution of our Buckle-Leverett equation. So as you see in the figures, that it closely matches with the exact solution, the both architectures. We also adjusted the mobility ratio of viscosities for this case, and then numerically compared them by using the root mean square error for metric and the training time. As you see, the accuracies are similarly close to each neural network's accuracy is similar. However, the training time is that MLP twice faster than CAN.
Use the pointer on the mouse.
This one. Okay. So After we verified our results with the exact solution, we need to make the validation with the real experimental data. So for this experimental data, we used the data from the experimental study of our one collaborator, Dr. Sarah Namambek. And for these cases, we adjusted the following mobility ratio taken from the experiment, and used it to train our neural network. So we implemented this in for CAN architecture. And firstly, we in this slide you can see that we used the following validation to see how the different optimization techniques impact on our performance of our Kolmogorov-Arnold network. As you see, that is where we use the only one optimizer fits perfectly for the first time step. But when we made the hybrid optimization strategy, it improves our prediction, closely matching for each cases. So by using this hybrid optimization, we made the following analysis validation. So we compared how the depth of the architecture impacts on the performance of the CAN. And as you see, that even in this depth architecture, the neural network predicts well, but compared to MLP, it little bit has a small bigger deviation. Then we added new layer and increased the depth of the neurons of each layer. As you see, that it perfectly matches with all the results. And also we compared our results, the results of the CAN model with our prior research with the MLP. With here we use CAN for the fixed diffusion term, and here we use the diffusion function, spatially dependent diffusion function, which was proposed from our prior study, which recently published also. And as you see that CAN with the fixed diffusion is able to match the trend of our MLP's diffusion function, which means that can generalize well to our results. So for this conclusion, to summarize, we evaluated the CAN model and performed it. We successfully implemented for the two-phase flow model. As you see, that CAN achieved comparable results. However, but it required more training time, and this hybrid optimization technique also improved our CAN performance. The deeper CAN architecture also improved and the match with the MLP's accuracy. To sum up, we can say that CAN is a viable alternative to use it to model two-phase flow in porous media. So that's all. Thank you for your attention. I'm happy to take any questions.
Thank you. We got time for questions. So, are there any?
Are you restore one-dimensional solution? Yes.
Yes.
Okay. And how did you choose function of the relative permeability?
The function of the relative permeability.
Yes.
Relative permeability, as I mentioned in this, I'll show you. Here, the relative permeability is this within this lambda. Lambda, as you see, the lambda is expressed as a ratio of the relative permeability and viscosity. And the relative permeability, as we choose the non-convex cases for fractional flow, we took the quadratic function, quadratic function of the saturations. of both phases. Yes.
Yeah, it's I think he's solving the buffer level, which is dimensions. Dimensions. So the certain terms will cancel. But still, it's square, so it's like.
Any other questions?
Non-complex.
Any other questions from the audience, online audience?
Okay.
Okay, thank you.
Thank you.
So the next speaker is Veronika Chepelenkova, and she is gonna give a online presentation. So I think it's time to try just to be sure that we'll see. Yeah, at least we can see the PowerPoint.
Do you hear me?
Yeah, we can see your full screen regime, so it works nice.
Okay, so hello everyone. Today I'm going to tell you about multi-GPU implementation of the numerical algorithm enhancing discrete element modeling performance. First of all, let me briefly tell you about the type of problem to be solved. We use discrete element method, or DEM for short, and here on the slide you can see two pictures showing scanned models of core samples. The left one contains multiple inclusions of material with different elastic properties, and the right one depicts the sample with only one material but having a complex shape of its pore space. Both of them are used to model physical tests showing sample behavior under finite loads. But DEM simulations are computationally intensive, so our goal here was to develop an efficient algorithm based on using GPUs on distributed memory systems and to measure its performance in strong and weak scaling tests. In DEM, the sample is regarded not as a continuous medium, but as a set of small particles interacting with elastic and friction forces, which can be represented as a system of springs connecting each two particles. To calculate the elastic force in normal direction, particles are allowed to overlap so that the difference between their initial and current overlap length is used in a Hooke's law as shown here. The friction force is calculated using the incremental representation of relative tangential displacement. It should be noted that some particles are considered as bonded, and there exists a critical length which breaks the bond if exceeded. More on bonded particles later on. So basically, we have Newtonian equations of motions for each particle, where the gravity force is neglected, and the interactive pairwise force is calculated among a specific subset of particles, J of I. To solve this equation, the velocity-Verlet finite difference scheme was used. Now, more on the subset of interacting particles. The most straightforward way to calculate forces of particle interaction is to sum up the forces for each possible pair of them, which sounds extremely inefficient and can be easily optimized knowing that most of the particles do not interact since they are too far from each other. To narrow down the area where forces are relevant, we construct a grid over a computational domain with its cell size chosen in such a way that at least one particle can fit into it. Now we assume that each cell knows about the particles lying inside it, and particles know the index of the cell they belong to. By doing that, we can define a subset of particles by picking all the ones inside 9 cells surrounding the particle of interest, including the cell it is lying at. This approach can significantly decrease the amount of interactions to be calculated. Next, about bonded particles. Let's say a pair of particles is defined as bonded if, after a packing stage, they end up being overlapped. This is an important definition since bonded particles interact with each other not only in a repulsive but also in an attractive way, as if there was some kind of cemented material gluing them together. Now for the packing stage. Here, the Poisson disk sampling algorithm is used to fill a given domain with uniformly distributed points, which are placed no closer than at a certain distance from each other. After that step, the radius within a given range is assigned to each point, and from now on, the Lobachevsky-Stillinger algorithm starts working. This algorithm is based on event-driven modeling, meaning that the next step is not defined as a fixed time, but rather the time of the next closest event, which is in our case the collision with either the wall or with another particle. Here on the slide, the formulae for times to the next collision are presented, and the closest event is obviously defined as minimum of all events. The next and final stage is uniaxial loading, and here we apply a finite stress to sample and measure its average stress and strain to use for calculating effective elastic properties. Now more on implementation details. On this slide, the overall particle structure is presented, and here you can see that it consists of a substantial number of properties, with some of them being pointers to arrays located somewhere else in the memory space. All particles are assembled to a list or an array, a part of which should be transferred between MPI processes. And the core problem is how to pack the structure to correctly transfer it. Casting it directly to an array of bytes is incorrect, as we will send only pointers and not the underlying data, which means the data will be lost and pointers will be invalidated because they are moved to another memory space, which can be either VRAM or RAM of another cluster node. Sending structure fields one by one will give correct results, but has extremely high computational cost, since calling transfer functions is an expensive operation and thus should be used as rarely as possible. So we've chosen to serialize data, meaning converting it to an array of bytes, not with general casting, but with placing inner arrays directly into a byte sequence to be sent. On the slide, you can see a diagram showing the process of serialization. On the top here is a schematic particle structure with pointers to other places in memory. When a particle is serialized, all pointers are replaced by the data they point to. The total list of particles can now be represented as a sequence of each particle byte stream. And the process of deserialization is performed in a similar way. This action allows us to call a transfer function only once, thus reducing the computational cost. So, to use our algorithm for distributed memory systems, we divide a computational domain to subdomains, each of which is assigned to a corresponding MPI process. And since the trajectory of each particle depends on the other ones, we have to add these so-called halo cells, that are the cells to be received from an adjacent process at each time step. And the major problem here is to handle particles moving through the boundary between processes. There are two possible variants here. Let's assume we are tracking the process 1, halo cells of which are highlighted in blue. The first situation is when the particle moves into the process and should from now on be handled by it. To do so, the process receives not only the particles in halo cells, but also the set of indices moved from an adjacent process to the one of interest. They are now added to the list of all particles in this process and are assigned to a corresponding cell of the first or the last row of grid. Similarly, if the particle leaves the subdomain, the process sends the array containing particles in its first or last row along with the array of indices of particles that should be now handled by another process. On the other hand, these particles should be deleted from the list in this process so that calculations are not doubled. So, the overall algorithm for each process at each time step is as follows. First, we calculate new positions for particles in the first and or last rows of the grid. Then we fill the arrays of indices of particles moved to another process. That gives us one array for each boundary, which is 1 or 2 in total. Then we serialize data and perform data transfer from VRAM to RAM. Next, we send the first and or last row of the grid to a corresponding process, and at the same time, we receive updated halo cells from the adjacent process. Now, if there exist particles moved through the boundary, we send indices of particle moved to the other process and receive indices of particles moved from the other process. If there exist particles moved to the adjacent subdomain, we remove them from the list of particles in a current process. And if there exist particles moved into a current subdomain, we add them to the list of particles and set corresponding grid indices. Now we transfer data back from RAM to VRAM, and deserialize it. It is also worth noting that the block of exchanging data runs simultaneously with the basic calculations for the rest of the subdomain, thus hiding the time needed to perform preparations and transfers. Now for scalability analysis. Two types of tests were conducted to measure the performance of the algorithm. The first one is the strong scaling test. Here we have a fixed domain containing 112,000 particles, which is distributed between 1, 2, 4, 8, and 16 processes. The efficiency is measured as a ratio of the time spent on a one process to the time spent on n processes multiplied by n. In the perfect case, efficiency should remain constant and be equal to 1, but in the real world, it inevitably decreases because of possibly uneven load distribution or communication overhead. This can be seen in the figure on the left of the slide. Here, from 8 processes and further, the data transfer becomes a bottleneck, which cannot be covered by major calculations. The reason for this is the too small number of particles, since the more processes, the less calculations per one process for the same amount of transferring. Another test is for weak scaling, when the domain is increased proportionally to the number of processes used. Here, the perfect efficiency can be reached when, no matter the number of processes, the program runs for the same amount of time, meaning that bigger size problems can be solved almost without any time losses. As it can be seen from the figure on the right, the implemented algorithm shows a nearly perfect efficiency in weak scaling tests. To sum up all of the above, in this work we developed and implemented a numerical algorithm combining both CUDA and MPI for multi-GPU computations on multiple computer cluster nodes. This algorithm uses both GPU and CPU simultaneously to reduce the time of calculations. We also proposed a method to exchange information about particles moving through inter-process boundaries, and conducted numerical experiments for strong and weak scaling tests showing the efficiency of the implemented algorithm. And that's all I wanted to say on this topic. Thanks for your attention.
Thank you for your presentation. We've got plenty of time to ask questions, so feel free.
Anyone has a question? Okay, I think here is okay. Yes, please.
Should I go there?
It's better to come here. Okay, here's a question. Okay, you can.
Yeah.
Okay.
Okay, thank you for your presentation.
Thank you.
Yeah. I was wondering, I saw this weak scaling part, that's it's hard to reach this. I was wondering about the speed up. Have you considered to compare like CPU computation versus multi-GPU computations, like traditional CPU versus this new model, with your CUDA implementation?
Oh, I did not perform these tests.
Okay, so then another question is, hopefully it works faster, right?
Yeah, sure.
Okay, how you deal, have some numerical questions. How you deal with the, you're solving unresolved discrete element method, which means is in one cell, you should have, you don't have this CFD, right? You have the purely, that's good. And regarding, you had this loading experimental work, right?
Yeah.
Did you compare your CUDA implementation with the experimental results?
We don't have any physical experiments on hand, so we've never compared it.
Okay, thank you.
Okay, I think we can go to next presentation.
Okay, great. So let's do it. So our next speaker is, and next and the last for the first part of our session is Sergey Solovyev, who is gonna give us a talk about spectral decomposition to solve elasticity problem. So Sergey, go ahead.
Excuse me, the quality of voice is not good
Sergey, we
here.
cannot hear you. We hear some strange sounds in there.
Oh. Hi, Sergey.
I think the internet connection is not stable, is it?
No, I think the problem maybe is with his or her microphone. Are you using any kind of hands-free or something? Maybe that's the problem. Okay. Again, she left. Um,
I think he is rejoining.
yeah.
Okay.
No.
No, it doesn't work again.
Is it setting or is it internet?
No, it's by. No, it's not internet. Okay.
He's gonna use the other computer, so probably in couple minutes he will be okay.
Okay. Professor Lipit. So until the next presenter will be ready, I want to remind you that you need to put your evaluation scores from the presentations, all the presentation of this session in an online platform. Do you know about this?
No.
Okay, I try to share the link for you in the chat box. Then you can join over there and put your evaluations.
Okay, great.
Okay, using this link, you can log in your account and then evaluate the presentations over there. Thank you.
Okay.
But generally, I think the last presenter has technical problems about his or her laptop or system. I don't know.
He's
if we
gonna
can...
come. He's gonna start. Yeah. Okay. We can see them.
Yeah. Finally, you make it.
I think the problem is something which I cannot fix. Okay, now you can hear me and you can see my presentation, yes?
Yeah, great.
Okay, great. Let's start. My talk will be about the solve elastic problem by static simulation and this slide about introduction. We want to solve the elastic problem in homogeneous medium with not constant coefficient, Lamé coefficient, and to solve this, we use we use the in 2 dimension. Okay, we use the rectangular mesh and find different approximation. The solution in this picture, you can see the point, the located solutions, the derivations, and after approximation, we get the system of linear equations, and want to solve it. How we solve? It's not big. It's not big problem. We use the conjugate gradient, but the main issue is how to check how to use the preconditional. What the preconditional we should to use. Now, in this presentation, in this work, we use the preconditional A0 as the matrix from the elasticity problem in homogeneous medium. The similar equation, but the coefficients are constant. And in the next slide, we want to say about how to solve this equation. We use the spectral decomposition to solve this equation. Why we do it? Because we can use the fast multiplications. We use the spectral decomposition in 1D, and after that we construct the decomposition for 2D and use fast matrix multiplications and very fast solve this problem. Okay, the first step is the simplify these equations when we don't use the constants. And the next step, second step, we come back, return to the constant lambda and mu. We will start from the description the first derivative. After that, move to the second, to the Laplace operator, and to the whole this equation. In 1D, the matrix for the first derivation has this pattern, and for the second derivation, this one, matrix A. The coefficients N and B, its coefficients N and B depend on type of boundary condition, Neyman, Dirichlet, or maybe third type of boundary condition. It does not matter. And we have the single decomposition of matrix B, and this decomposition correlated with the eigenvalues of decomposition of matrix A for this matrix. Okay, here properties of these matrices. And next step, we move from 1D to 2D. At first, we write the 1D. In 2D, we write the matrix for the first derivation along horizontal lines, and second derivation along to the same horizontal lines. And this matrix is B, B single line and A single line, contain of diagonal blocks, the same diagonal blocks. Each this block described on the previous slide. Next step, we look at the second direction. Second direction, the first derivative due by z and 2d by z2, and we can construct the Laplace operator from these two matrices. Also, we can use the SVD, single variable decomposition of matrix B from previous slide, and so get the representation of matrix A hat for Laplace by the product of some matrices, matrices of V, single line, V double line, and diagonal matrices D. So if our problem is Laplace operator, so we can inverse very fast this matrix, because matrices V are orthogonal and V are diagonal. Anyway, we have the elasticity problem, not Laplace problem, and here you can see that the diagonal part are Laplace, and off-diagonal operator of mixed derivations. Anyway, for each operator, we can write the matrices, which presented on previous slides, B single line, B double line, and also we can replace these matrices by single variable decompositions, like here, this by this and this by this. So we can represent our operator by matrices with orthogonal matrices V and diagonal orthogonal matrices V, orthogonal matrices W, and diagonal matrices D. So the initial system of linear equation A equal B and initial matrix A can be replaced by matrix. We can perform decomposition matrix A by product of V tilde, V hat, A hat, and V hat transpose. And to solve problem AU equal B, we need to solve this system of three equations. The first and third problem, it's not problem, equation is not problem to solve because V hat is orthogonal. So we concentrate on inverse matrix A hat. Matrix A hat has the diagonal blocks, D diagonal blocks, and pretty full dense of diagonal blocks. But of diagonal blocks we don't inverse, we don't construct explicitly, we just construct the algorithm how to product of diagonal blocks. And to inverse matrix A hat, we will use the conjugate gradient. This slide about how fast get product of any matrix V with single line by vector U. Any matrix V single line, W single line, A contain of diagonal blocks, the same diagonal blocks. So we can replace the product V by U by product the diagonal block V by any matrix U, where each column of matrix U is part of vector U. And the result, matrix V, where each column of matrix V is a part of vector V. As a result, we replace left computation, left product matrix by vector, but by right product small dense matrix by small dense vector, dense matrix. It's very good because in our program we use the gem functionality of BLAS library, and this gem functionality is very highly optimized for computational resources for any method. And based on fast multiplication, we can construct the fast product of matrix A hat by any vector, because diagonal blocks are diagonal, and off diagonal blocks can be product on some multiplied off diagonal blocks on some vector by product sequential product of each matrix V, D, and W using by gem operation. Okay. As a result, we construct from initial A equal B this system with V hat, A single line, and other. So solve this algorithm. Algorithms can consist of 5 steps, and the third point is the most hard, because we should invert the matrix A one single line. And to do it, we use the conjugate gradient algorithm, and we need just 10 maybe maximum 20 iterations to converge this conjugate gradient algorithm. After that, we come back to the original system with the coefficients lambda and mu, and use the same algorithm. And our numerical experiments we perform on this cluster with 256 gigabyte RAM. And the first experiment, we want to know what's the largest system we can solve by our approach. And the large system is about 1 billion nodes of meshes, and so it is 2 billion unknowns of system of linear equations, and depend on boundary condition and depend on contrasts of coefficients. The solution time it's not more than 4 hours of this system. Of course, if for Dirichlet boundary condition, solution time less than for Neyman boundary condition because of conditional number. On this slide, you can see the convergence of our iterative process. It's also shows that Dirichlet boundary condition with the same coefficient very faster than Neyman. And here we want to observe how the solution characteristics of our algorithm depends on number of meshes in computational number of nodes in computational meshes. And the first results, which are very good, is that number of iterations does not depend on size of mesh and a bit decreasing. And computational time, of course, increasing, but not critical. And at the final slide, we want to compare our solver, iterated solver, with spectral decomposition with some direct solver from MK library, mathematic kernel library. And of course, the memory consumption of our solver much less than direct solver. And for solve 1 billion mesh nodes, it's not need 256 gigabyte RAM. It's enough 128 gigabyte RAM. But direct solver cannot solve this problem, of course. And for computational time, also, our approach much faster than the direct solver. And so our conclusion that we developed very fast algorithm. We can solve very big problem, elasticity problem with constant coefficient, and this algorithm can be used as preconditional for the elasticity problem with inhomogeneous medium with not constant coefficients. Thank you for your attention.
Okay, thank you for your presentation. So, are there any questions, comments?
You have question? Okay, here. Yeah.
Okay, Sergey, thank you for your presentation.
Thank you.
Can you hear me? Okay. So
Yes,
what do you mean by direct solver? Do you mean Gaussian elimination method, or do you mean when you compare with a direct solver?
Yes,
Do you mean?
I mean
You compare
that. I understand your question. For our solver, in our implementation, we use the BLAS library, the gem function from MK BLAS, mathematical kernel library, Intel MK BLAS. So for direct solver, we also use the direct solver Intel MK Pardiza, which of course based on LU decomposition with some preliminary step like reordering step and other tricks to the special direct solver Intel MK Pardiza, and we use this solver.
Okay, then another question. Have you tried to use maybe some modified conjugate gradient method to speed up, like preconditioned conjugate method or some other kind of things?
We can try use
Yes,
without the preconditional, but it's not effect. With special precondition, there are different preconditions. Like
yeah, of course. I mean, they might help you, but that's it.
Probably it can be effect, but you mean about, for example, multigrid? Yes. Or
Yeah. So it's pretty good result compared to direct. You have a good computational time, right, compared to direct solvers. Yeah. And
yes.
if you have
Not
maybe. Yeah.
Not we don't try the special preconditions, but it in our plan compare our solver with iterative solver with special precondition from some library like from PETC library. PETC. Do you know PETC library? So
Yeah, I've heard that. Yes.
Yes.
Yeah.
Yes. It's just in our plan, but not now. Thank you.
Okay, thank you.
That's it. Thank you very much.
Thank
I think
you.
we're done.
Yeah, we have finished with our first part of mini symposium.
Thank you. Sorry for
let's
problems.
thank all the speakers again, and we are supposed to be back here in 3 hours, right? So we continue at.
Yeah, I think we can finish the
2
session
p.m.,
here.
right?
Yes.
Okay, great. So thank you and see you.
Thank you very much.
Okay.
Thank you.
Bye.
Где-то 6 часов летели. Вам, скорее всего, 8-7 летели.
6,5.
6,5. Ну да. Да. Ну, тогда в 2, да, увидим, скорее всего. Дальше.
Ну, да, если придется еще.
Да. Старайся.
Hi. You need